All right. Got through chapter 4, I think, last time. And then after that, we went to maybe chapter 11. If not, we'll go to chapter 11 now. And in chapter 11, we talked about a couple things. We talked about really electrons, and we talked about sort of how energy and electrons, as they move from different energy levels, that they can be excited to a higher state of energy and will eventually kind of relax themselves back down to a lower state of energy. That energy that comes off is the form of a wave. And remember that the speed of light is equal to the wavelength times the frequency. And the wavelength in this case is in meters. The frequencies in reciprocal seconds are a hertz. And that equals our speed of light, which is meters per second. 2.997, I think they use here, times 10 to the 8 meters per second is our speed of light value. We also saw that the relationship in terms of energy associated with these waves can also be found by E is equal to H times the frequency. H is a constant, that's Planck's constant. 6.63 times 10 to the minus 34 joules times seconds. That is again the frequency here. And reciprocal seconds are a hertz. And that is a one-to-one relationship between those two. A reciprocal second are a hertz. Remember, you can tie both of these equations together. So E is equal to hc over the wavelength. And what that allows you, if you know the wavelength, you basically figure out the energy as both of these are constants. And again, obviously, if you have the frequency, you can figure out the energy associated with that wave. So both of those are sort of associated together. We talked about the idea of moving away from Bohr's model of the atom, where in Bohr's model of the atom, he had these electrons in these orbits moving around on these different energy levels. To this idea of electrons really don't move in that sort of fashion. They do move sort of randomly around the atom, and a more quantum mechanical sort of model of it. And remember that as we have n equals 1, that is the ground state, that is the lowest in energy. Anything above that, n equals 2 through 7, those are higher in energy. Those are sometimes referred to as excited states. And electrons move from one energy level to the next, either upwards or downwards, as we talked about in this quantized sort of way, which means that they always will sort of gain or lose enough energy to fully transition from one energy level to the next. They'll never find their way sort of halfway between or anything like that. If you remember, we sort of talked about that as like stairs. So again, usually, you're on this stair, this stair, this stair. You're never between steps or anything like that. And same thing with the electrons. They will either fully sort of transition from one to the next, and they will gain or lose enough energy to do so. In addition, as they sort of release this energy, as they transfer from, say, higher energy to lower energy, they sometimes will give off that energy. And depending on where it falls in the electromagnetic spectrum, and that was the spectrum where, for example, we have like gamma rays on one side, X rays. We got our visible part of the spectrum where we see colors, that Roy G. Biv. Actually, going in that way. And, down here we got something like radio waves and so forth. Remember that in terms of the relationship between waves and energy, the longer the wavelength, the lower the frequency, and also lower in energy, which would be on this side, as opposed to over here where we have a shorter wavelength, a higher frequency, and a higher energy associated with it. So that again is the relationship between sort of those things. And again, as electrons transition from one energy level to the next, we do see again things may come off in different parts of the electromagnetic spectrum. Again, if we do see color as part of the visible spectrum, could have the infrared spectrum or the UV after it's here as well, where you may not see color and stuff like that. Remember as well, these colors also have sort of an arrangement in terms of energy. Although I wrote it kind of backwards here on the paper, red is actually a longer wavelength and lower in energy than violet, which has a shorter wavelength and a higher energy. So even again within the colors, there is a difference in energy. And it could also, depending if you see the different colors, you can make an estimate of how maybe far that electron is traveling. So if you see more of a, say, violet color coming off, that probably is an electron traveled a good amount of energy levels because that's going to release a good amount of energy to do so. If you see more of the red color come off, then maybe that electron only transitioned a shorter period of time. We then got into really sort of that quantum mechanical sort of model and this idea that really the best that we could do is sort of have a probability of where to find an electron. We really don't know how it's traveling, where it's at any given point in time, but the best that we could do is sort of there's a high probability that you could find an electron in a certain area of the atom. Usually that's around the nucleus since it's positively charged, electrons are negatively charged. But again, we have no idea of how it's traveling or where it's located. That's the Heisenberg uncertainty principle, that the more you know about its location, something like an electron, the less you know about how it's traveling and how it got there. So this led us into really electron configuration. And remember, electron configuration, there are s orbitals, and there's only one type of s orbital which could hold a maximum of 2 electrons. There are p orbitals, and there are 3 types of p orbitals that could hold a maximum of 6 electrons. Remember that when we do have more than one orbital, we do sometimes refer to it as a subshell or sublevel. There are d orbitals. There's 5 different types of those. Could hold 10 electrons max. And there are 5 types. And lastly, there are f orbitals, which can hold 14 electrons max, as there are 7 individual types of f orbitals. And there is a specific order at which electrons go into the atom and they fill into the atom. And as we talked about, that is always lowest energy to highest in terms of how the electrons go in there. Remember that you could kind of create the sort of order yourself on the paper by just remembering where each of these start. And remember that the S starts on the first energy level. P orbitals don't appear until the second energy level. D orbitals don't appear until the third energy level. And F orbitals don't appear until the fourth energy level. And what that allows you to do is you basically could just kind of make a little chart like this. 1s down to the right a little bit, 2p, 3d, and then down there 4f. And really at that point, all you have to do is just fill in the numbers underneath it. So 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 4f, 5f in this case. And there you go. And remember that we always start this way and then keep coming through the arrows. And that gets you basically your order here. And so if we were writing electron configuration for something like carbon, which is 6, we would start at the top there, 1s2, 2s2, 2p, 2 there, overshot it there, 2p2. And that would be the electron configuration for it. Remember, the first number is the principal quantum number. That's the orbital it's in. and that's how many electrons are in the orbital or subshell. We also talked about drawing what is known as the orbital diagram, which are boxes, are lines that represent each of the orbitals, and 1s, 2s, 2p. And remember that when they go into these boxes, first one always goes up, second one always goes down. First one up, second one down, and then here up. And we do go up, 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 and then go back and pair off when we do that. So the idea there is no individual two electrons should have the same four quantum numbers, so they always go sort of opposites in there. Remember that when we get to the transition metals, it is the order here 4s, and then you go back to the 3D. And again, that also affects what happens, as we talked about with transition metals. When they lose electrons, they will always lose those s orbitals first, electrons, and then the d's if necessary. Representative elements will always just kind of lose the last ones there. Any questions on that there? Now, I believe in this chapter as well, we talked about some periodic trends towards the end of it. And it's a reminder of some of those periodic trends. I'll just draw a big boxy periodic table. There we go. So when we talk about periodic trends, the first thing is effective nuclear charge. The effective increases as you go to the right and decreases as you go down. Remember that effective nuclear charge is the positive charge that the outer electrons feel as a result of screening. So if we have a valence electron and there's electrons in a lower energy level, instead of feeling the full positive charge of the nucleus, they get screened out from that positive charge and they only feel like a lesser charge, which is why they can be removed. Ionization energy increases as you go to the right and decreases as you go down. Ionization energy is the energy required to remove an electron from an atom. And again, it gets harder to remove electrons as you go to the right. We also have electron affinity. Increases as you go to the right, decreases as you go down. Electron affinity is the energy change that happens when somebody gains an electron. And the higher electron affinity means that they're pretty good at gaining electrons and accepting electrons, and it sort of increases to the right. And electronegativity, I think, as well. We talked about electronegativity is the ability of an atom to bring electrons towards itself. Remember that fluorine is the most electronegative element you could have. So that also increases. And then we have, lastly, atomic size, which is the only one that decreases as you go up and to the right and increases as you go down and to the left. And all these trends, as we talked about, basically is why we understand what happens as we go up and to the right on the periodic table. We have a lot of things that are very small that hang on to their electrons. It takes a lot of energy if you want to try to remove electrons. They like to bring electrons towards themselves. So that's why nonmetals typically like to gain electrons. As you go left and down on the periodic table where you have metals, you have all these things that like to give away their electrons pretty easily. You don't have to convince them to get rid of those electrons. They're bigger as well, so the electrons are further away from the nucleus, not held as tightly, and you can remove electrons pretty easily, which is why metals typically lose electron. Any questions on that there? So I believe that was chapter 11. Let's then go to chapter 12. And in chapter 12, we talked about bonding. And we really talked about two types of bonding. We talked about ionic bonding and covalent bonding. And remember that ionic bonding is always between a metal and a nonmetal, where the metal will transfer an electron over to the metal. That's going to create a cation for our positively charged guy, an anion for our nonmetal. And remember, in an ionic bond, there is actually no sharing of electrons here. It is that positive negative attraction or electrostatic attraction that holds that together. And that's very different than in covalent bonding when we have two nonmetals. And because the two nonmetals, again, are located pretty much in the same spot on the periodic table, they all have very similar periodic trends, which means they both want to hang on to their electrons and not really get rid of them. So what ends up happening here is we get some sharing of electrons. And that sharing can be equal sharing. And that is what is referred to as a nonpolar bond. Or it can be unequal sharing, which is referred to as a polar bond. Now we can use Lewis dot symbols to help us understand sort of what's going on in both of these types of bonding. So when we talk about ionic bonding, we have something like lithium, which is group 1 on the periodic table. It has one valence electron. Will react maybe with chlorine that has 7 valence electrons. Remember that the number of valence electrons equals the group number. So the number of valence electrons equals the group number. And in this case, what's going to happen is this lithium is going to send its electron over. If we look at the electron configuration here, 1s2, 2s1. Over here for chlorine, neon, 3s2, and 3p5 in this case. And the result of that is that's when lithium is going to gain a charge, and the chlorine here will accept it, the electron, and become negatively charged. The result of that is the whole purpose of bonding, as we talked about, is for everybody to become very stable and reach that noble gas configuration. And what happens when lithium does that is it ends up at 1s2, which is the same electron configuration as helium. And chloride actually ends up at neon's configuration, and they both achieve noble gas configuration. And again, it's the positive negative attraction that holds it together. Remember that when we draw ionic bonds, we do want to include the positive and negative charges in our pictures because they are ions. There's no sharing of electrons that is happening here. Remember, in covalent bonding, we can kind of determine what type of bond we're going to get by using the change in electronegativity values. Remember, they run from 0 to 4. And if you have a difference in electronegativity values of 0 to 0.4, that is considered a nonpolar bond. And that is covalent bond sharing of electrons. If you have a difference in electronegativity of like 0.5 to less than 2, that's going to be a polar covalent bond, unequal sharing of electrons. And usually if you're above 2, that's going to be an ionic bond. Remember as well that you don't always need the actual values, that you could use the periodic trend to make a determination if it's going to be polar or not, especially if you are comparing something in the same row on the periodic table or the same group. If you're comparing somebody on the same row on the periodic table and there are opposite locations, the one furthest to the right should be more electronegative and also give you a polar bond. If you're looking at the same group up and down, the one that's higher up should be more electronegative and you should have a polar bond. So again, if you had something like HF, H like 2.1 and F like 4 in terms of electronegativity values, again, that's going to get you a 4 minus 2.1, which is a 1.9. That's definitely a polar bond. The result of a polar bond is you have this unequal sharing of electrons that you could demonstrate with that arrow, that dipole arrow. Also means that essentially the fluorine is going to be more partially negative because the electrons are hanging out over there. And the hydrogen can be more partially positive because the electrons are kind of moving away from the hydrogen within the bond. In a nonpolar bond, it's basically a neutral bond. equal sharing of electrons, so you really don't get a side that's more positive or a side that's more negative because of that equal sharing of electrons. Also remember that you really don't need the electronegativity values to determine if something is an ionic bond, because if you have a metal and non-metal, that's all you need to know, and it's going to be an ionic bond, so you really don't need those numbers for that. Any questions on that there? So then we talked about really kind of drawing Lewis structures for covalent bonding. And remember that if we, let's see here, let's do, when we have basically sharing of electrons, the first thing that we want to do is count up the total number of valence electrons. And in this case, we would have 4 for the carbon. We would have 3 times 6 for the oxygen. Remember, if something has a charge, you do have to add that in. So the -2 would mean you need to add 2 electrons. If you had a positive charge, it means you should subtract whatever the charge is. That's going to give us 18, 20, 24 valence electrons. Remember that the least electronegative is in the center. And remember that hydrogen and fluorine are never in the center in that sort of situation. So in this case, we would go C, O, O, and O. Remember that what you want to do is basically just make a single bond to each of the outside ones. So 1, 2, and 3. Each of those lines represent 2 electrons. So that is 6 electrons total. If you subtract that off from your total here, got like 18 more to go, I think. So we're going to go on the outside in pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Remember that everybody needs to follow the octet rule, which is 8 electrons, except for hydrogen, which should only have 2. So no more than 2 on the hydrogen. At this point, we used all 24 of our electrons. The last thing that we do want to do is check to make sure that everybody has met the octet rule, and if they have not, then we want to kind of fix it. So in this particular case, carbon is short. It only has 6. So to fix the octet rule problem here, we do try to make a double bond to fix it. In this case, you could go from any of them. When we do make a double bond, remember, or even a triple bond, we are bringing electrons in to do that. And in this case, we would end up with a structure with a double bonded oxygen there. And we usually do put a little bracket around it with a -2 charge. And in this case, we now have 24 electrons, and everybody will have basically 8 electrons around it. This is also something, as we talked about, that you could draw what's known as a resonance structure. So you could have absolutely double bonded on the left-hand side there. Look exactly the same, obviously, except that you have double bond on the left, single bond up on top. Or you could have double bonded to the right-hand oxygen and single bonded the guy on top, and could draw any of those 3 sort of structures. You do want to kind of follow those steps because that usually should lead you to a pretty good structure. You don't want to kind of do piecework where you're kind of drawing this. We then talked about sort of geometry with this, and there's 2 types of geometry. There's electron pair geometry, and there's molecular geometry. And when we do geometry, which is known as VSEPR, valence shell electron pair repulsion model, we basically have a couple of rules, but really the main rule is any double bond or triple bond, when you're counting them, they count as a single bond and single pair of electrons. So basically everything counts as 1 when you're doing geometry. And the simplest geometry that you could have is a diatomic molecule. So if you have basically a diatomic molecule like hydrogen, the geometry is always going to be linear. And it doesn't matter if it's single bonded, double bonded, triple bonded, if it's 2 of the same elements, 2 different elements. If you have only 2 elements involved, it is going to be linear geometry. When you have three or more sort of involved, you do have to look at um, how many electron pairs there are and how many bonds. And we kind of made a table for three or more. You want to look at the central atom always, the number of electron pairs. You want the number of bonds. And this will give you an electron pair geometry name. And we'll have a molecular geometry name, our shape. And for example, if we have two electron pairs, two bonds, looks something like this. And again, it's always the center atom that you want to kind of count around. And that would give you a linear geometry and a linear molecular geometry. I guess we could go bond angle as well, about 180-degree bond angle. We then also talked about a geometry of three electron pairs and three bonds, so something that maybe looks like so. That would be trigonal planar and also trigonal planar for both of those names. Has a bond angle about 120 degrees. Then we talked about a molecule with four electron pairs around the central atom and four bonds. So it looks something like this. And with that, it would be tetrahedral is the electron pair geometry, and tetrahedral for the molecular geometry. And as you can see on all these here, they got a bond angle about 109.5. They both have the exact same name, and that's always the case when you draw your Lewis structure and you have no dots on the central atom. If you have no dots on the central atom, then both of those names will be exactly the same. It is only when you have non-bonding electron or dots on the central atom that the names are different, and the name that ends up being different is the geometry name. The molecular geometry name is the one that changes. And we saw one where we had three electron pairs and two bonds only. And it would look something like, for example, we'll do this. And in this particular case, the electron pair geometry would be the same. So it has three electron pairs. Again, remember the double bond counts as one, two, and three electron pairs. And in terms of bonds, one bond and two bonds there. Oh, that was where I put those right down there. That's how we got there. Now, when we talk about the name for the electron pair geometry with three electron pairs, it's still going to be trigonal planar. But because of those non-bonding electrons, the molecule actually moves a lot more than it can with an actual bonded atom there. And we get something that's known as angular or bent angular. And this has a bond angle of less than 120. The next one that we talked about was something with four electron pairs and three bonds. And something like that will look like, do that. A, A, and A. And coming through here. Again, with four electron pairs there, it's going to be tetrahedral for the electron pair geometry, as that name does not change. But again, with that extra kind of electron pair and no bond, we end up with a shape that's known as trigonal pyramid. So trigonal pyramid. And the last one in terms of geometry that we had was four electron pairs and two bonds. And it'll look something like this. Come that way. And again, with four electron pairs, it's still going to be tetrahedral for the electron pair geometry, but this is going to be bent or V-shaped. Like water is an example of that we saw. Both of these will have less than 109.5 for the bond angle. Any questions on that there? And remember, up on Canvas, there's a chart I made of all these things, and obviously it's in your book as well. We finished up this chapter on bonding, talking about molecular polarity, which again is different than bond polarity. So bond polarity, we use kind of difference in electronegativity values to help us understand if it's the overall molecule or the bond is polar or not. When we talk about molecular polarity, we're talking about the entire molecule as a whole. So the one place where bond polarity will equal molecular polarity is in diatomic molecules. So again, if you have something like hydrogen, this is a nonpolar bond. And because that's the only bond in the molecule, this would also be a nonpolar molecule. If you have something like HF, that is a polar bond. And once again, because that's the only bond in the entire molecule, it would also be a polar molecule. When you get to three or more atoms, you have to look at two things. You have to look at, are there polar bonds? And the molecular geometry of the molecule or the shape of it. And remember that you can have a molecule that has polar bonds but be nonpolar. The example of that is CO2 that we talked about. It has polar bonds heading towards the oxygens, but because the geometry here is linear, they will essentially cancel each other out. You basically have oxygen pulling to the right and oxygen pulling to the left, and basically like two people pulling on a string equally in opposite directions. They cancel each other out. As opposed to water, where also has polar bonds, but because of its geometry of being bent or V-shaped, it is going to allow those sort of those polar bonds to actually add to each other, and you get a net dipole moment happening in this direction, where the oxygen side is more negative and the hydrogen side is more positive on water. Remember, nobody wants to draw these vectors, so there are what we talked about, basically symmetrical geometries. And for you guys, that's basically trigonal planar or tetrahedral. And again, we're talking about the molecular geometry here. And basically what these guys have in common is no dots on the central atom. And if you have no dots on the central atom and all the outside atoms are the same, it will be a nonpolar molecule pretty much. Remember, though, if you change one of the outside atoms to something different, it will then become polar. So if you have this situation, but all the outside atoms are not the same element, you will then make it a polar molecule. So that's sort of the exception to that one. Then we have some unsymmetrical geometries. And for you guys, that's the angular. That is the trigonal pyramid. That is the bent or V-shaped. And pretty much what these guys have in common are dots on the central atom when you draw your Lewis structure. And if they're all the same element on the outside, then that molecule is going to be polar. And that's a really quick way to do sort of molecular polarity by looking basically dots or no dots, and is everything on the outside the same or different? It's a very quick way you could kind of do that. Any questions on that there? All right, that wraps up chapter 12. We then went to backwards, I think, and we went back to chapter 5, I think. And chapter 5, we talked about nomenclature and naming, and talked about a couple different types of naming. We had type 1, which is an ionic compound, and that means it's a metal and a non-metal, and that means that we have basically, again, a cation and an anion happening. And to name type 1, and whenever you're naming, if there is a metal involved, that is the most important thing. And if the metal falls in group 1, 2, 3, or if it's zinc, cadmium, or silver, what they all have in common is a fixed positive charge. So when we have this situation, all you have to do is go the whole name of the metal. And remember that the non-metal pretty much gets the IDE treatment at the end of it. So we just drop the last part of the name and put IDE. So obviously here, something like NaCl, that is group 1. So that is sodium chloride in this case. We also talked about type 2 naming, also ionic, also metal and non-metal. Once again, metal most important. That is going to be a transition metal. And basically what they have is a variable positive charge. So what we do with this is pretty much the same thing. We still use the whole name of the metal. We do include a Roman numeral for the charge on that positive metal. And then our non-metal is the same with the IDE treatment at the end of it. So in this case, if we had something like FeCl2, that is a transition metal, and that means we do need to figure out the charge. So iron, I'm not sure what the charge is, but chlorine is group 7, which means it has a -1 charge, and that means that's a -2 overall. It needs to balance out to 0, so the iron would be +2 in this case, and we would have iron Roman numeral 2, and again, chloride. Remember that we never mix Roman numerals or prefixes together, and you should never have a prefix with a metal that's involved. So that's always the wrong move. We then talked about type 3 naming our compounds, and type 3 are actually covalently bonded stuff. That's between two nonmetals. And speaking of prefixes, this is where we do use the prefixes. So we do use those prefixes like mono, di, tri, tetra for 4, penta, hexa, etc. And the coding kind of pull rules are we do not use mono on the first name, but it is okay on the second. And we do sometimes drop the vowel off the end of the prefix if we get like an A and an O that comes together, or two O's that come together. So again, in this case, if we had N2O, these are two nonmetals. Here we go with our prefix for 2. There's no charges or anything to worry about. So di, we do use the whole name of the first element. Second guy is named like normal with the IDE treatment, and this would be monoxide here. So dinitrogen monoxide in this case. Again, prefix and prefix. We then talked about polyatomic ions. And remember, polyatomic ions are groups of nonmetals together that have a particular charge associated with them. NO3 minus, that is nitrate. Remember, the way you could kind of remember some of these is it is all about how many oxygens or the different number of oxygens. And NO2 minus is nitrite. Usually the one with more oxygens in a group will end in ATE. The one with the least number of oxygens will end in ITE in that case. There's also groups of four that are related to each other. The popular one that we see, ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Remember that we could kind of break this group of four together by breaking it up here in terms of our oxygens. These have the lowest, so this would be chlorite. The one with the lowest in a group of four, you also start with hypo, and then this would be chlorite. To the left there, this would be chlorate, and the one with the most in a group of four starts with per and ends with 8, and this would be perchlorate. You could also substitute the chlorine for any of those halogens, and they kind of name the same way. So instead of chlorate, it could be bromate if you had bromine in there as well. Remember that probably the best move on these, as we talked about, is, kind of learn one of them, like again, the eights or the ites, and just know how to adjust it. So remember, the charges never change if they're related to each other. The only thing that changes is the oxygens. So if you knew nitrate had 3 oxygens and you needed nitrite, all you have to do is just drop down 1 oxygen, or vice versa if you're kind of going upwards. This led us into sort of how these things are sort of named. And since a majority of all of the polyatomic ions are negatively charged, typically speaking, these guys end up with a metal and a polyatomic ion. And typically speaking, we usually will just follow type 1 or type 2 rules with it. Either you'll need a Roman numeral for the metal or not. For the polyatomic ion, doesn't matter how many you have of it, it is still just the whole name. Again, we don't use any prefixes or anything with those. The other consideration when you're writing the formula for a polyatomic ion is if you have more than one, you do need to put parentheses around the polyatomic ion, and again, put the little number on the bottom there as to how many you have of it. The last thing we talked about in terms of naming was acids. And remember, acids naming all involve whether or not there's oxygen involved. And if the answer is there is no oxygen, then it will start with hydro something ic acid. So HCl, no oxygen involved. Acids typically will have the aqueous symbol next to it, is how you know you're kind of talking about the acid. And here this would be hydrochloric acid. If it does have oxygen, it usually will contain a polyatomic ion in it. And if your polyatomic ion ends in 8, then your acid name will be something ic acid, like HNO3. That's nitrate. This becomes nitric acid. If your polyatomic ion ends in ITE, it will be something OUS acid, like HNO2. Nitrite, nitrous acid. So that's pretty much your acids. And again, it's really all about whether or not there's oxygen or not. Any questions on that there? That wraps up chapter 5. Then I think perhaps, I'm not sure where we went, but we'll go 6 next. Why not? Chapter 6. Actually, I think we went 8, but we'll go 8. Chapter 8, we talked about grams and moles and Avogadro's number. So remember that sort of our conversions from between these things, Avogadro's number is 6.022 times 10 to the 23, and that equals 1 mole of something. And the units associated with Avogadro's number can vary. They can be atoms, They can be molecules. And really, we use Avogadro's number as a conversion factor to go from basically moles to atoms or molecules are backwards. And remember that you don't want to use Avogadro's number uh, unless it does mention something about that. So if there's no mention of atoms or molecules, probably you should leave it on the side. Probably the conversion we use the most is molar mass. And molar mass, again, comes from the periodic table, and it is the number on the bottom. So for example, here, hydrogen would be 1.008 grams per mole is the molar mass of hydrogen. Remember that we could use that as a conversion factor. We could flip it around to do some dimensional analysis and put it that way. And remember that molar mass is really the conversion between grams to moles or moles to grams. So if you have grams, you want to divide by the molar mass from the periodic table, and that will get you moles. And if you have moles, you want to multiply by the molar mass, and that will get you grams, as those guys will cancel out. And again, that is a very common, obviously, conversion that we use a lot. If it is more than one thing, you just add up all the parts. So if you had H2O, you'd go to periodic table, hydrogen is 1.008 grams per mole, and you times it by 2, and oxygen is 16 grams per mole. That gives you a molar mass for water of 18.02 grams per mole. The number always stays with the grams part, and it's always per 1 mole. The other thing that we talked about is really important when you do molar mass is if you have something in a balanced equation that has a coefficient, you do not take the coefficient into account when you're calculating the molar mass. The molar mass is always calculated just solely based on one of the formulas by itself. So H2O, again, if you had an equation where you had 4 in front of it and you wanted the molar mass, you do not use the 4. The molar mass of water is still 18.02, regardless of what the coefficient might be in that balanced equation. The other thing that we sort of talked about in this chapter, obviously, in doing these sort of conversions is we talked about a couple of different types of formulas. We talked about the empirical formula and the molecular formula. And remember that the empirical formula is the simplest whole number ratio of what is present. And the molecular formula actually tells you exactly what is present in terms of the elements. So for example, if I had C2H6 as my molecular formula, that is a relationship of 2 carbons for every 6 hydrogens. That is the same relationship if we reduce it down to 1 carbon for every 3 hydrogens. And that would mean that CH3 would be my empirical formula. So if you're given sort of a formula that is the molecular formula and you want the empirical formula, if you could reduce it down, the subscripts on the bottom, which are actually moles here, if you could reduce these guys down to whole numbers, that will give you an empirical formula. Sometimes you cannot. So if you have something like water, that is 2 hydrogens for every 1 oxygen. That is as low as you could go. So both the empirical formula and the molecular formula will be the same. All ionic compounds are empirical formulas. We also talked about how to calculate these things, and to calculate the empirical formula, first thing you want to do is take, if you're given the percent composition by mass, you want to assume 100 grams. And what that does, as we talked about, is essentially just turn the percentages into numbers, and that will give you the grams of each element. You have the grams of A and the grams of B. What you would then want to do is convert using the molar mass to moles. So percent composition to grams, grams to moles. Once you do that, you want to divide by the smallest number of moles. So let's just say again, for example, you ended up with 2 moles of A in the previous step and 4 moles of B. In this case, you would divide everybody by 2 moles, which is the smallest, and you would end up with 1, you'd end up with 2. And if you do end up with whole numbers at this point, that would give you your empirical formula. Now, if you do the division and you do not end up with whole numbers, remember you do need to multiply it by a number to get to a whole number. So again, if you ended up with 2 moles of A and 5 moles of B, you divide it by 2 moles. You end up with 1 and you end up with 2.5. And that would give you AB 2.5. This is no good because that does need to be a whole number. But again, if you take 2.5 and you times it by 2, that does give you 5. So you would times everybody by 2 here. And you would get A2B5 would be your empirical formula. Remember, in order to round to the whole number, it has to be really, really close to the whole number, like 1.99 or 2.01, something like that. If it typically ends in zero point 0.5 when you divide or 0.33, that's usually too far to round. You do have to kind of find a number to multiply everybody by. We also talked about molecular formula, and basically, to do the molecular formula, you basically need three things. You need the empirical formula, which will either be given to you or you got to calculate it. You need the molar mass of the empirical formula, which you need to calculate. And you need the molar mass of the compound. And that is usually given to you in the problem, in a book problem. So usually that is given to you. So somewhere in the problem, they'll say, hey, this has a molar mass of like 140 grams or something like that. And what you do is you take the molar mass given to you of the compound, you divide it by the molar mass of the empirical formula, and that's going to give you a number. And that number that you get is what you would then take and multiply your empirical formula by. So if we just got a 2 when we did that, our molecular formula for this guy would be A4 B10. Would get us to our molecular formula by multiplying each of those by 2. In terms of rounding to a whole number, you could be a little bit more generous in your rounding on this calculation because it should be a whole number multiple. Any questions on chapter 8 there? Okay. Then I think maybe we went to 6, I think. 6 was a very short chapter. It was basically about equations and balancing equations. And remember that we have our reactants, which is our starting materials, goes to our products. And basically, when we balance an equation, we have to have the same coefficients, the same numbers of elements on each side. So if we had something like this, remember that you can make like a little table of the elements, and you got your reactant side, your product side, and we got 2 nitrogen on the left, 1 on the right, 2 hydrogens on the left, 3 on the right. So to fix the nitrogen, we only balance equations by putting coefficients in front. So we would put a 2. That's going to give us 2 nitrogens and 6 hydrogens. We could then go to the left, put a 3 there, 2 nitrogens and 6 hydrogens. And now we pretty much have, again, a balanced equation. A couple of things we talked about. Remember that you can use a fraction to balance the equation, but you do have to get rid of the fraction. When you're all said and done, all your coefficients that you have in front of something, they all need to be whole numbers, and they need to be the simplest set of whole numbers. So again, if you ended up with a balanced equation that looked something like this, and this was balanced with these coefficients, you could actually go through and reduce everybody down by 2, and you should do that to get the properly balanced equation in that case. The other thing that we talked about in terms of balancing was if you have polyatomic ions that are the same on opposite sides of the arrow, it's sometimes easier to keep those polyatomic ions together and just balance them as kind of polyatomic ion units. And oftentimes that makes it a lot easier to uh, balance the equation. And questions all in chapter 6 there. That then led us into chapter 7, which was really about types of reactions. And remember that we basically have two big categories of reactions. We have double displacement reactions, and we have redox reactions. And they both account basically for the three reasons why a reaction takes place. Remember, either you form a solid, you form water, or electrons transfer. Those are basically your three reasons a reaction takes place. Double displacement reactions always have this setup, AB plus CD. These are two ionic compounds. And basically what always happens is we switch partners and we make new ionic compounds on the other side. So we end up with AD and CB here. And in this particular case, this takes care of two of the three reasons why a reaction takes place. Either you form a precipitate or you make water. And the two sort of subcategories of this type of reaction is a precipitation reaction, where you do form a precipitate, and a acid-base reaction, where you form basically water. So for example, if we took some sodium chloride and we reacted with some silver nitrate, we will get some silver chloride, which is a solid, plus some sodium nitrate here. And this is a double displacement reaction. Basically, our partners switch places. It formed a solid, which is a precipitation reaction because of that. Again, if you had something like HCl, hydrochloric acid, plus some sodium hydroxide, that's an acid and base, also a double displacement type situation. Will always form water and a salt, which in this case is sodium chloride. And we always get water and a salt. And again, the reason why this reaction takes place. So a precipitation reaction and acid-base reaction are specific classifications of a double displacement reaction, where basically one you form a solid and one you form basically water. Redox reactions are really about the transfer of electrons, and remember that oxidation means that you lose electrons. Reduction means that you gain electrons. And basically what falls under this category are synthesis reactions, which are two things that make one thing. Decomposition reactions, one thing breaks apart into a couple of things. Single replacement reactions, one thing comes in and kicks out something else. And combustion reactions. So all of these are specific ones basically for combustion. You just need oxygen in most cases. And in each of these cases, there are electrons being transferred is essentially what is happening in this case. Remember, in the case of a precipitate being formed, we use our solubility rules, right? To help us decide whether or not these things will make a solid. So things like that have nitrate are soluble in everything. Things from group 1 are soluble in everything. Acetate soluble in everything. Chloride, bromide, iodine are soluble in everything except for silver, lead, mercury. So there's all those kind of rules that we talked about that help us decide whether or not we will get a solid. The other big thing that we talked about in this chapter was there's a few different types of equations that we sometimes write to represent what's going on. So if we took something like our silver nitrate plus our sodium chloride, which makes our silver chloride plus our sodium nitrate. This is again what is known as the molecular equation. We could write what's really happening in this reaction, which is if we have a strong electrolyte, it will completely break apart into ions. So something like silver nitrate is a strong electrolyte. It will break apart into silver and nitrate. Sodium chloride is a strong electrolyte, breaks apart into a sodium and chloride ion. Anything that is a solid, liquid, or a gas typically will stay together, so we don't break those apart. So we do keep them together. And anything like ionic compound typically will kind of break apart, like sodium nitrate is also. This is what is sometimes referred to as the total ionic equation, or the complete ionic equation. And remember, in this equation, you could look on both sides of the arrow, and you should be able to find ions that look exactly the same. And these ions here are what are referred to as spectator ions. They are basically just there watching. They're not involved in the product formation. We could cross them out on both sides. And what that leaves us is the reaction that is truly happening here, which is the silver from the silver nitrate will go find the chloride from the sodium chloride, and they will form this solid here. And this is what is referred to as the net ionic equation. And those are the three types of reactions that you could write, especially for double displacement reactions. You could also write them for single replacement reactions, but typically double displacement reactions here. Any questions on that there? So remember, anything that's considered a strong electrolyte, which completely breaks apart in solution or water, will get broken apart. Anything that's a weak electrolyte will stay together, and you don't break it apart. Anything that's solid or a liquid or a gas typically will stay together. Any questions on that there? All right, then I think that was pretty much 7. Then we went to 9. And 9 was everybody's favorite thing, right? Stoichiometry. Right. And pretty much in 9, we talked about basic stoichiometry. So if you have an equation, you could take the coefficients as conversion factors. And you could say, for example, for every 2 moles of A, I get 3 moles of B. For every 2 moles of A, I produce 2 moles of C, and so forth. And when you have a basic stoichiometry problem, there's really 4 steps to do. You want to always balance the equation. You want to convert whatever they give you to moles. You want to do the actual stoichiometry part, which is the mole to mole relationship. And then you want to do moles to some other unit. And it's really these 4 steps just followed in that order. So, for example, if I had 5 grams of B, and I want to know how many grams of C would I produce, my steps would be to balance the equation. I would take my 5 grams of B in this case. I would use the molar mass of B, and I'm just going to say that that's going to be 2 grams per mole. You get that from the periodic table, obviously, would be our molar mass. We would go with 2 grams per mole here of B. And again, that's kind of like our second step there. That's going to get us 2.5 moles of B produced. We would then go and do our mole to mole relationship between B and C. And from the equation, 3 moles of B will give us 2 moles of C. And again, that is nothing more than just the coefficients. So we would take our 2.5 moles of B, Remember, we want to get rid of B, so opposites cancel. So 3 moles of B on the bottom, 2 moles of C up on top, and 2.5 times 2 divided by 3, going to get us a 1.67 moles of C. At this point, we can then use the molar mass of C to convert it into grams, and I'm just going to say it's going to be 10 grams per mole for C. So we'll go 10 grams per mole for C. It gets, obviously, you get that from the periodic table. And obviously, here to finish out, we would just times it by 10. It'll give us 16.7 grams of C would be produced in this case. That again would be our 4 steps. That also would be our theoretical yield, right? And the theoretical yield is your maximum yield based on the equation and the stoichiometry that you do. Remember, if we have limiting reagents, we basically still follow those 4 steps. We balance the equation, we convert to moles, and here we do a limiting reagent sort of calculation, and then we continue on our mole to mole, and lastly, our moles to some other unit. Remember, to do a limiting reagent calculation, you will know the moles of each reactant you started with. So let's just say we had 4 moles of A and 2 moles of B. And what we want to do is just a calculation. We'll use this equation here, which was 2, 3, and 2. 2A plus 3B goes to 2C. And what we would do to figure out our limiting reagent is we would take our 4 moles of A. We would do a relationship between our 2 reactants. 2 moles of A, 3 moles of B, gonna get me 12 divided by 2 is 6 moles. B is needed. And what we would do then is compare our moles needed to our moles that we started with. And in this case, we do not have enough. So that would mean that this is our limiting reagent. This is our excess reagent. And we would obviously continue the calculation with our limiting reagent in that case. Now, other options we talked about is you could just do 2 separate calculations between your reactant and your product. And whichever one produces the least amount of product is your limiting reagent and your theoretical yield. So you could do it that way as well. Now, we also talked about percent yield in this chapter, and percent yield is the actual yield divided by the theoretical yield times 100%. And the actual yield is usually given to you in the problem. So somewhere in the problem, they'll say how much you actually produced. The theoretical yield, you need to usually calculate either a regular stoichiometry problem or a limiting reagent problem. And when you divide it, obviously it gets you your percent yield. Usually we're looking for a high number on that, but less than 100. Also, you know it's a limiting reagent problem when you could get the moles of each reactant. So just based on the information given to you, you can pretty much get to the moles of each reactant, and that's how you know it is definitely a limiting reagent type of problem. Any questions on that? That was chapter 9, I believe. All right, so we did 10, I did 11, we did 12, so 13, which I think is gases, I think. Chapter 13. So gases, pretty much we had a bunch of gas laws. So we had our friend Boyle, which was P1 V1 equals P2 V2. Remember that 1 atmosphere equals 760 millimeters of mercury and 760 torr. This is at constant temperature. We had Charles' law, which is V1 T1 equals V2 T2. This is at constant pressure all gas laws Kelvin for the temperature always. We had Guy-Lussac's law, which is P1 T1 equals P2 T2. This is at constant volume. Again, Kelvin for the temperature. We had our friend Avogadro, V1 N1 equals V2 N2. This is at constant temperature and pressure. We had the Granddaddy of them all, which is the ideal gas law, which is PV equals nRT. That is the most restrictive. It's got to be atmospheres. It's got to be liters. It's got to be moles. It's got to be Kelvin. And that's because R is a constant that you always have, which is 0.08206 liters atmosphere Kelvin mole. And we also talked about a couple other things. STP, that is standard temperature and pressure, 1 atmosphere, 273 Kelvin. Remember that if you happen to be at STP, you can use a conversion factor. 1 mole is equal to 22.414 liters. Remember that you could only use that conversion if you're at STP. Otherwise, you do need to go into the ideal gas law. And then really we had the combined gas law, which is P1 V1 T1 is equal to P2 V2 T2. And that's our combined gas law. Remember that the combined gas law is the winner of all gas laws because if you remember this version of it, as we talked about, all you have to do is basically scratch out whatever is not given to you or whatever is constant. So for example, if we had no moles given to us or temperature, we scratch it out and now we have Boyle's law. Again, you could basically do that for anything that is constant, not given to you in a problem. You could just remember this equation and you could get them all, including the sort of ideal gas law. You can scratch out one side and it's equal to R, which is a constant. And again, if you had no pressure or moles, you could scratch them out and you could get Charles' law. So that's a really good one in that situation. Remember that the more collisions, the higher the pressure, right? Less collisions, the lower the pressure as well. Any questions on that there? All right, lay that up there.